Welcome to Module 8. For this lecture, we'll be working with a fast simulation that differs quite a bit from the demo problem we worked on in the webinar. Here, we'll be working with a two-dimensional aquifer as opposed to a one-dimensional column. The hydraulic conductivity distribution is now heterogeneous. We will be including reactive mineral surfaces in this simulation. The problem is based on our earlier Freak-C model for elevated metals in acidified groundwater at a former industrial site. Here we'll be setting up the initial conditions for reactive transport and then seeing how we can model a proposed remediation approach for the site. Without getting into too much detail, I will mention that groundwater flow heterogeneities do play a role at the site. To represent this for our purposes, I've used a correlated random field generator to posit a distributed mix of high hydraulic conductivity and low hydraulic conductivity zones. I'll note that this issue is more three-dimensional in character at the real site. This figure shows the distributions of log hydraulic conductivity values generated, with blue colors indicating sandy materials and brown colors more silty and clayey sediments. The black dots are simply the seed points with log K values used to initiate the random correlated field generator. Here we define the two-dimensional model grid in the FAST transport input file, and we use the XYZ flag to tell FAST that hydraulic conductivity is to be interpolated from a text file. The format of the text file is shown on the right. This is simply the output from the random correlated field generator. The initial acidified solution composition from our earlier example and the mineral assemblage and reactive surface definitions that went along with it are assigned across the entire model domain as an initial condition. This is pretty straightforward using the chemistry initial conditions keyword block in the transport input file. The specified head boundary conditions on the left and right sides of the model imply groundwater flow from west to east. The resultant steady state flow field, as impacted by the heterogeneities, is shown on the figure on the left. The contour lines represent groundwater elevations. The arrows indicate local groundwater flow vectors, with the longer, redder arrows associated with the highest flow velocities. As you would expect, flow is enhanced in the blue shaded areas and muted in the brown shaded areas. The results make sense hydraulically. The specified head boundary condition on the left edge of the model is associated with an unimpacted groundwater composition, the same pH 6.8 water that was used as an initial condition for the earlier Freak-C example in Module 5. The idea is to simply run the reactive transport model forward in time for a decade without any perturbations to let the system sort itself out spatially, with acidified, metals-impacted groundwater in the less permeable portions of the aquifer to remain and therefore act as a lingering source of contamination. In contrast, the most permeable portions of the aquifer near the upgradient edge of the model domain, this would be the left side, are largely swept by inflowing water associated with the boundary condition. This is represented by the distribution of dissolved iron concentrations shown on the figure on the right. You see pretty similar distributions here for dissolved aluminum shown on the left and sulfate shown on the right. Concentrations are plotted in moles per kilogram of water. Here, we see more or less the same pattern repeating for some of the trace elements that complex with iron, aluminum, manganese oxide surfaces, as these constituents now have a substrate to adsorb to once again. And the examples include chromium, arsenic, and nickel. These plots are kind of interesting. Here we're comparing model results versus data for arbitrary pairs of solutes. The data represent real samples collected from site monitoring wells where the solutes are subject to both geochemical reactions as well as chemical transport. The FAST results also reflect the influences of the same mechanisms. The general agreement between the model and the data here is encouraging, but a more complete analysis is warranted and is something I need to look into. With all of this as a background, if we're satisfied with the initial conditions model, the next step is to simulate the proposed remediation pilot test. This test entails the injection or introduction of calcium and magnesium hydroxide slurries to raise the groundwater pH and to reduce trace metal concentrations, either by subsequent readsorption or as direct precipitation as metal oxides. To simulate the test, a source term is added that is activated after 10 years elapsed time. The source term consists of a background, this is a non-acidified groundwater, augmented with either calcium hydroxide, portlandite, or magnesium hydroxide, brucite. And sure enough, after 120 days of testing, things seem to be working. Iron and aluminum hydroxides do reprecipitate near the injection locations, as you can see here, indicated by the arrows. And the trace elements are locally removed from solution by complexation back onto the newly precipitated hydroxide mineral surfaces at these locations. The problem with this, from an engineering viewpoint, is that tens of tons of calcium magnesium hydroxides are used in this process. So this scheme is still being worked on for this site. Beyond reprecipitation of the iron, aluminum, and manganese hydroxides near the injection sites, which is desirable, additional mineral precipitation reactions may occur. And this may be of some concern for in terms of potential aquifer pore clogging and reduction of permeability, which would impact future injection. Calcium carbonate may precipitate at both injection sites as a consequence of the local pH increase, for example. Calcium sulfate in turn is predicted to precipitate near the calcium hydroxide injection site only. The latter is of particular concern because the model precipitated mineral mass is fairly significant. So, with all of this in mind, I have a challenge exercise I would like you to look at. Environmental consultants involved with this project have discussed the issue as to which is the most important process: reabsorption of the trace metals onto the precipitated hydroxide phases, or direct precipitation or co-precipitation of some of the trace metal hydroxides, such as zinc hydroxide, copper hydroxide, and so forth, as a result of the pH increase from the reagent augmentation. So, with this in mind, try to redesign the FAST model to take this latter issue into account. One suggestion would be to remove the surface definitions altogether and focus on the saturation states of the various metal hydroxides or oxides. Good luck.